Okay, morning everyone. Let's get started. So first of all, we'll release the homework 5, our last homework assignment today. You might have been able to see the assignment on Canvas if our TAs have already uploaded. But anyway, they're going to show up on Canvas today. And the major task for homework 5 is to implement the backpropagation algorithm and also test your understanding about backpropagation, right? So I have some bonus question asking that if you can implement logistic regression, which we're going to discuss in a lecture of next Tuesday. So, but it's up to you. The most important task will be backpropagation. So again, I will suggest everyone to start early because it's approaching the end of semester. I guess many of you have to prepare several final exams, right? So we'll have some final exam online, but the workload for that is pretty light, as long as you can understand the basic concept we've discussed throughout this semester. There won't be any issue. We'll spend some time reviewing what we have discussed at the last lecture. Right? By the way, just a reminder, please start homework 5 early, and also be aware that we also need your submission of final project report. And unfortunately, we cannot grant extension for final project because we have to submit your final letter grade to the administration given some deadline. The deadline won't be changeable. Okay, so starting today, we're gonna talk about another paradigm of machine learning, which is called Bayesian learning. Right? So my research focus is Bayesian learning. Unfortunately, for this particular class, we can only spend 2 or 3 lectures, give a very brief general introduction of Bayesian learning. So if you're interested in specifics about Bayesian learning and also what is cutting edge, you're welcome to register my class called Probabilistic Machine Learning in the spring. Okay. So to introduce and to explain why we would like to introduce Bayesian learning, right? So let's see what we have saying so far, right? So first, in terms of the objective or the goal of doing learning, right? We have saying mistake-driven learning, right? We would like to update our model to avoid making mistakes in predicting training examples, right? So typical example is the perceptron algorithm, which is online mistake-driven learning algorithm, right? Or least mean square regression, right? So for linear regression, we want to find a set of model parameters which make our prediction error to be as small as possible. In other words, we want to minimize the training loss, right? This is also like mistake-driven. We want to make minimal mistakes in predicting the training examples. So expect that when we see future examples, we can make smaller mistake as well, right? So it's a mistake-driven. And then we discussed about, in theory, how we associate the training error with the generalization error, right? So our previous or intuition is that, okay, if I can do well in fitting the training data, that means I can make my model predict training data very well, then I'm very likely to predict the future examples, right? The unseen examples. That means we by default assume that the smaller training error will lead to a smaller generalization error, right? But when we use some computational learning theory as a framework to characterize the relationship, we found that we miss an important component. Okay. What's that component? Think about the generalization error bound we have discussed previously, right? in the agnostic learning framework. Right? This is probably the most general learning framework we have discussed so far. So so the generalization error bound tells us the generalization error or true error, right, is upper bounded by the training error, okay, plus some term determined by the VC dimension, right? So the VC dimension actually characterize how complex your learning algorithm is, right? More specifically, how complex or how expressive your hypothesis space is, right? So usually we'll see some kind of trade-off, like you choose a complex hypothesis space, meaning a richer hypothesis space, will give you smaller training error, right? Sometimes it can even go down to 0. But it doesn't mean like you can really generalize well, right? Because there is another important component which relates to the complexity of the hypothesis space you use, right? If it's too complicated, then you still have a big gap term here, right? That's why in the algorithm design or in the machine learning model choice, right, we have to consider the trade-off between the model complexity and fitting of the training data, right? It's not like, okay, the better I fit the training data well, the better I have the smaller generalization error I will have, right? So you do need to consider the effect caused by model complexity, right? So that's why looking at this PAC learnability and computational learning framework is useful, right? It actually gives us the insight about which factors are important for the generalization error, right? It's not only the training error, although training error obviously is the most intuitive factor we consider first, right? But we also need to consider model complexity. So these are about how we build up a learning framework, right? Whether choose to fit to the training data only, right? This is called empirical risk minimization, right? And then if we can also consider the trade-off to the model complexity, we usually add some regularization term in our objective training objective function, right? Does it make sense? Right? Remember what is SVM's training objective? We have a regularization term, square norm of the weight vector, right? Then plus the hinge loss, right? The hinge loss is over the training data reflecting how well you fit the training data, right? But SVM tries to minimize the summation of this regularizer and the hinge loss, right? So they seek for a best trade-off, right? Or best balance, right? So this is called a regularized risk, empirical risk minimization, right? And based upon these two frameworks, we have seen various learning algorithms, right? And such as online learning, stochastic gradient descent, and the greedy heuristic search, like in decision trees, right? And in all cases, we assume our learning algorithm will generate a function that produces a label y given the input feature vector x. Right? Okay, so how would we like to add something to the framework and organization about learning algorithm, learning model we have discussed, right? We're going to introduce another way of thinking about what does it mean to learn, right? Which is called Bayesian learning. You'll see that Bayesian learning uses a probabilistic view for hypothesis-based search. So remember, nearly all of our previous learning algorithm is some kind of determinate search procedure, right? You're given a hypothesis space, then you define a loss function, right? You optimize this loss function. This optimization drive you to search over the hypothesis space and find out the best hypothesis, right? That's the idea, right? But what if we reformulate this learning procedure as some Bayesian inference procedure, right? Then learning amounts to, or learning is converted into finding the most probable hypothesis across a distribution over the hypothesis space. Right? I will talk about why this is meaningful and this is useful, right? Taking such a view, right? And then we will introduce two specific Bayesian learning algorithm in this regime. One is called logistic regression. One is called naive Bayes. Especially logistic regression is very, very simple. You can view it as a generalization of the linear regression we discussed early in our semester, but it works surprisingly well in many applications. For example, online advertising, right? The modern online advertising system, they're gonna have some feature mapping, pre-processing, embedding, learning, all kinds of stuff, and then all those kind of millions or even billions of features are usually through into a large logistic regression model, like at the end of the production line. Okay, so here's our plan for today's lecture. So we'll first explain Bayesian learning framework. We'll introduce two notions of Bayesian learning. One is to learn a probabilistic concept, namely target function is to learn a probability rather than to predict a label, a decisive label. And then we'll introduce two commonly used framework in Bayesian learning. One is called maximum A posterior estimation, also known as MAP estimation. The other is maximum likelihood estimation, MLE estimation. So if you have taken any statistical class before, you might have already heard these two types of estimators. Right? Then we'll give two concrete examples for maximum likelihood estimation. One is based on binomial distribution. The other is based on normal distribution. Okay, first, what is Bayesian learning? Right? So as we mentioned, we're going to introduce two different notions of probabilistic learning. Right? Let us first look at the first notion, which is relatively more straightforward. Right? The first type of Bayesian learning is just to try to learn a probabilistic concept. So what does it mean for probabilistic concept? Right? So all the previous classifiers we have seen is try to learn a mapping, right? Try to find a hypothesis which can map your input feature vector to a label, right? Either -1 or 1, right? It's kind of a decisive label. I give you an example. I just tell you, okay, you should predict label as 1, or you should predict label as -1, right? But now what if we want our prediction that can reflect some kind of uncertainty or confidence. Right? For example, suppose I want to predict whether the stock price NASDAQ index is going to increase or not today, right? This is a binary classification problem, right? You can use SVM, you can use neural networks, you can use perceptron, whatever classifiers we have discussed. Given us a list of features, right? Perhaps a stock prices in NASDAQ, right? You can predict 1 or -1, right? Increase or decrease, right? But now if I want more than that, right? I want you to reflect or give me some kind of confidence given the data, given the features. What is the confidence, or what is likely, what is the chance that the NASDAQ index will increase today? Right? In that case, like just giving a +1 or -1 won't be sufficient, right? I want to know, okay, how probable you will give 1, right? How can we get such kind of prediction, right? We can change our target function or concept from predicting a decisive binary label to predict a continuous probability. Right? Namely, given X, I'm gonna predict the probability that your NASDAQ index is gonna increase today. Like maybe 0.6, maybe 0.7, maybe 0.99, right? If it's 0.99, maybe we can buy some stocks, right? Or maybe just 0.1, right? Then, given this probability, right, we can make our own rules to decide whether we think we're gonna make final prediction to be 1 or -1, right? Maybe say I can put a rule like if it is bigger than 0.5, then I'm gonna give a label 1, right? If it is less than 0.5, say 0.2, I'm gonna give a label -1, right? But again, you have the flexibility to define the rule, right? So you can combine your own knowledge, your experience, your rules of thumb to decide how you're gonna give the final label, right? And this learning will only give you a probability. Right? That will make your learning more convenient and more informative, right? So to learn such a probabilistic concept, it is essentially learning a function that maps the input feature vector to a continuous value, right? But this continuous value is restricted to be 0 and 1 because it has a probabilistic interpretation, right? It represents the chance that you have label 1, right? Rather than just label 1 and -1, right? So that means any regression framework we have previously used can be considered here, right? What you need to do is just to make sure that your output is always a number between 0 and 1. Does it make sense? Right? We'll come to some specific examples for this type of method later. That is logistic regression. Right? But does this framework or does this formulation sound reasonable to everyone? Any question? Okay. So now let us talk about another notion of Bayesian learning, which is more general, in that it will talk about how we're gonna do hypothesis search, right? So we know that the general learning paradigm essentially is a searching procedure. You define a hypothesis space, which could be finite, it could be infinite, right? You have to define some kind of laws to drive your search procedure and find out the best hypothesis, right? And Bayesian learning actually provides a probabilistic criterion in searching and selecting a hypothesis, right? Remember, it just use a probabilistic view to describe the searching procedure, but the hypothesis itself could be deterministic, could be learning a probabilistic concept. It doesn't matter. Okay. Only the criterion for selecting the hypothesis is probabilistic. Now let us look at how we're going to formulate this idea, right? So the goal for Bayesian learning is same as the goal for other learning paradigm. Our goal is to find the best hypothesis from some designated hypothesis space H, right? Using some training data D, right? So this is the goal, right? And in Bayesian learning, they're gonna define the best hypothesis as the most probable hypothesis in H. How can we fulfill that? how can we describe or quantify what does it mean for most probable hypothesis, right? We're going to first assume a probability distribution over the whole hypothesis class, H, right? It's like, this is your hypothesis space, right? You can imagine every point, every dot in this hypothesis space represents a particular hypothesis, which could be some function, right? Then we assign a probability distribution over this whole space. That means every point in this space will have some either density or point mass, right? Probability mass, right? And then we also need to know something about the relationship between the data observed and hypothesis. Meaning that we need to know that, okay, how can we characterize the relationship for any hypothesis? So this is a hypothesis space. And the observed training data, right? And then we're going to build up a probabilistic model to represent those associations, right? For the distribution over the hypothesis space, we're going to call it the prior distribution over this hypothesis space. And then the relationship between the hypothesis and data is usually modeled by the so-called likelihood. Okay? That is, given this specific hypothesis, namely some kind of function, right? How likely you're gonna have this training data, right? And you can imagine for that, for some hypothesis which kind of very highly deviated from the training data, then this likelihood will be very small, right? And for some hypothesis which is close to the ground truth, you know, it is very likely that it is this hypothesis who generates the data, right? So you should have some high likelihood, right? So you're gonna combine your prior or the hypothesis with likelihood given each hypothesis the data generation, right? To determine what is the posterior distribution of the hypothesis given the data. Right? That's briefly what Bayesian learning is formulated, right? We'll come to that into more details later, right? So why do we choose such a framework, right? Bayesian framework to formulate hypothesis searching, right? It provides interpretable learning algorithm. Why? Because you can assign the prior distribution, right? You give the prior distribution which encodes your prior knowledge, your rules of thumb, your preferences, whatever, right? So it injects some meaning on that, right? And also, you specify how, given the hypothesis, how likelihood the data is generated, right? It also enforces you to give some explanation, right? You can't say, okay, given this hypothesis 1, it will give a very high likelihood, and given hypothesis it doesn't give a high likelihood, right? You need to explain why. And it also provides a rigorous framework that combines prior knowledge with the observed data, right? This prior knowledge can guide the model towards something we know, right? And finally, because it is based on probabilistic theory, right? Merit theory, all kind of stuff. So we have a very rigorous and comprehensive tools for learning and analyzing learning, right? And also it can integrate uncertainty of the learning results, right? I can tell you, okay, I not only tell you, okay, what is why I should choose this particular hypothesis. I can also tell you my uncertainty of choosing this particular hypothesis. Why? Because that framework allows us to calculate or at least approximate what is the posterior distribution of the hypothesis given the data. Right? It's a distribution, not just the point. Okay, so now to get into the details, let us first review Bayes' theorem, right? So this is the foundation of probabilistic method, right? It's called Bayes rule or Bayes inverting rule, right? So it tells us if we want to compute the conditional distribution of y given x, we can first compute the joint probability of x and y, right? Then we divide this joint probability by the marginal probability of x, right? And this joint probability can be further decomposed as the prior of y multiplying with the likelihood of x given y. Okay, that's the if we want to write it in more detail, Bayes' theorem just tells that, okay, for any possible values that y and x can take, right, the probability that given x taking this particular value small x, your random variable y takes the particular y is equal to this guy divided by this guy, right? So now, if you look at the structure of the Bayes' theorem, right, especially in a numerator, right, we see that, okay, if we want to compute the conditional probability of y given x, right, sometimes we can call it posterior distribution, namely when we observe x, what is our distribution of x or y, right? This posterior distribution is determined by two terms, right? One term is the marginal probability of y, and we often call it prior probability. That is, what is our belief in y before we say any data x, right? And the second term that determines the posterior distribution is the so-called likelihood term, which is here, right? P of x given y, right? Which characterize the likelihood of observing x given a specific choice of y, right? Then we'll combine the prior probability with the likelihood, which measures how your choice y will fit the observation of x, right? We can get the posterior probability. That is, what is the probability of y given that x is observed? Okay. In other words, this theorem tells us that the posterior is proportional to prior times likelihood, right? So here are some kind of rules about probability, which we have previously covered. So we can quickly go through them and stimulate our memory, right? So we know that there's a product rule. If we want to calculate the joint probability of two events, A and B, right? So this just means A intersection with B, right? It is also denoted as a joint probability of A and B, which can be written as the marginal probability of B multiplying with conditional probability of A given B, or symmetrically, the marginal probability of A times the conditional probability of B given A, right? And if you want to compute the probability of A union with B, right? So remember, this is not A intersection with B, right? It just tells, is this represent another event that is A happens or B happens, right? Then you need to add the probability of A plus probability of B and subtract it by their joint probability, right? This can be represented by the Venn diagram, right? We got A and B, right? If you want to compute the probability of A union B, right? You just add up probability A, area over A, area over B, subtracted by their overlapping area, right? And if we say two events A and B are independent, that means their joint probability is the product of their marginal probabilities, respectively. Or equivalently, their conditional probability is the same as marginal probability, right? And also, we have this total probability formula that if we have n mutually exclusive events, right, and their summation is 1, then if we want to compute a marginal probability of not even B, we can just add up the joint probability of B with each AI, right? Okay. It can be further decomposed as P of AI times the conditional probability of B given AI, right? Okay, any questions so far? Assume everyone feels comfortable and straightforward. Okay. So now let us try to apply the Bayes rule in hypothesis search, right? As we mentioned, right, the learning essentially is to find a best hypothesis H in a hypothesis space given the training data set D. Okay? So in Bayesian learning, we use the so-called posterior probability that H given D. So H actually is a binary indicator. H is 1 means that H is the true hypothesis. Right? Of course, H can be any hypothesis in a hypothesis space, right? Any dot in this inside this circle, right? So we want to look at what is the posterior probability that H hypothesis given the D is a true hypothesis, is a target concept, right? They want to pick up the hypothesis whose posterior probability is the largest. Like we move that kind of hypothesis is the best hypothesis in a space. Does it make sense? Right? So again, P of H given D is a posterior probability, which answers what is the probability that H is the true hypothesis. This particular H is true hypothesis, given we have observed data set D. Okay. Again, here, both H and D are events. D means the events that we observe this particular training data set. And H is the event that the hypothesis H is the true hypothesis or is the true concept, right? And then we can apply the Bayes rule, right? According to the Bayes rule, this posterior probability is determined by, first, the prior probability that H is the true hypothesis, right? Before we see any data, what is our prior probability, a prior knowledge, a prior confidence, prior belief that each particular H is the true hypothesis, right? And this is also where we can inject our background knowledge, our rules of thumb, our domain knowledge, right? If we don't have any information, we can choose this P of H as a uniform distribution, meaning that, okay, I believe before I see any data, every hypothesis is equal likely to be the true concept, right? But if you do have some kind of domain knowledge or preferences, you can design your own prior of that, right? And the second term that determines the posterior probability is the likelihood, right? P of D given H, which measures the probability that this data is observed given the true hypothesis is H. So what, in other words, like given your true hypothesis is this particular quadratic function, what is the likelihood you observe our current particular 10 data points, right? And you can imagine for different hypotheses, right? This likelihood could vary, right? Some hypothesis which really doesn't explain the data set will have low likelihood, and some hypothesis which close or well explain data will have some high likelihood, right? And eventually, we just need to normalize the numerator by this marginal probability of data D, right? What is marginal probability you observe this data D? You can see that it's actually is independent of any knowledge of H, right? So actually it's constant to H. That means if we really want to find out which hypothesis H that maximize this posterior probability, actually P of D is some constant you can ignore, right? It has nothing to do with your maximization procedure. You can just throw it out. Okay, any questions so far regarding our Bayesian learning foundation for hypothesis searching? Everyone feels comfortable? Great. So now let us look at the two commonly used framework for Bayesian model estimation. One is called maximum A posterior and map estimation. The other is called maximum likelihood estimation. Right? So given some data, right, some training data D, right? As we mentioned, right, we want to find the most probable hypothesis. In other words, we want to find out which hypothesis has the maximum posterior probability to be the true hypothesis, given the data D, right? So to get such a hypothesis, we say we're trying to find a maximum A posterior estimation. Right? This is called map estimation. In other words, we want to maximize this posterior probability from the whole hypothesis space H, right? How can we do that? We just apply the Bayes rule, right? We know that this posterior probability can be written as prior of H multiplying with the likelihood of the observation given H divided P of D, right? And so mentioned P of D is a constant to H. So you just get rid of it, doesn't affect your maximization, right? So you can just throw it, then map estimation amounts to maximizing the prior multiplying with the likelihood, right? So this is called a maximum A posterior hypothesis, right? We denote the estimation by H map. Right? But also there could be scenarios that you don't have any prior preferences over the hypothesis, right? As we mentioned, in that case, a commonly used approach will be, okay, I'm gonna assume P of H is uniform, okay? In other words, equal, before we see any data, every hypothesis has equal chance to be the true concept. In that case, P of H is proportional to a constant, right? Then when we in that case, if we want to find a best hypothesis, we only need to maximize the likelihood, right? So we call this kind of hypothesis as a maximum likelihood estimation, right? In other words, maximum likelihood estimation can be viewed as a simplified version of the map estimation, in that in the maximum likelihood estimation, we don't put any prior information on prior preferences over the hypothesis. That means to find the best hypothesis, we just need to maximize the likelihood. And from computational perspective, directly maximizing the likelihood itself or product of the prior probability with the likelihood usually can cause numerical instability. That's why we usually take a logarithm over them, because you take a logarithm is a strictly monotonically increasing function. So you take a logarithm with that, doesn't affect your optimum at all. Okay, so this is the two common strategies, map estimation and maximum likelihood estimation. Any questions so far before we proceed to two concrete examples? Okay, great. So now let us see two examples of maximum likelihood estimation. One is called Bernoulli trials. The other is called normal distribution. So Bernoulli trials are usually used to model binary observations or binary data. And normal distribution is commonly used for continuous observations or real valued observations. Right? right? So remember that if we want to perform maximum likelihood estimation for hypothesis search, right? First we need to define the hypothesis H, right? And then given every hypothesis in H, right? You need to define a model, right? Which can tell us what is the likelihood given a particular hypothesis, the observed data, right? So let us look at a concrete example. Suppose you are hired by a CEO from a startup, right, to do your first consulting job, right? And CEO asks you a question, right? My company makes light bulbs, right? And I need to know what is the probability they are faulty so that I can optimize my manufacturing and dispatching procedure, right? And you say, okay, sure, I can help out. Can I make sure that they're all identical, meaning that we're produced in exactly the same production line, right? And CEO will say yes, right? And then you respond, excellent, I know how to help. We need to do some experiment, right? Then you asked the manager to random pick up 100 light bulbs, right? And test them, right? And given some electricity, you find out, okay, 80 bulbs work and 20 fail, right? Then you just tell the CEO that, okay, the probability the light bulb you produced is 0.2, right? And CEO says, how do you know that? Right? Yeah, how are you gonna respond to CEO? How do you explain to the CEO that you know the probability of failure is 0.2? So I guess you're saying like because I got 20 failure out of 100, so the ratio is 0.2. Well, that might be a little bit too straightforward. They'll see that they'll feel like, oh, that's too simple. That's I pay too much for this, right? Right. You need to give a more systematic, more principled explanation for that. Yeah, let's take a look at this. Yeah, indeed. If you divide 20 by 100, you get 0.2, right? But why this 0.2? This kind of calculation is well justified. We're going to justify it in a maximum likelihood estimation framework, right? We're going to do that, right? First, as we mentioned, right? If you want to conduct maximum likelihood estimation, you need to first model what is likelihood, right? So first, assume that our failure probability to be P, which is unknown, right? Then the success probability will be 1 minus P. And you will the testing of each light bulb as a Bernoulli trial, right? Meaning that there's a binary random variable, as you just suggested, right? It's binary random variable. It has a chance of P to fail, right? A chance 1 minus P to work. Right? And we're doing this set of trials IID, meaning that every test is independently and identically distributed. Right? Then we model the output of each experiment as a Bernoulli distribution. Right? Then if we do it for 100 times, then what is the probability that you say 80 works and 20 don't? This is the probability of a multinomial, not multinomial, the probability of multiple Bernoulli experiments, right? All of 100 tests, you got 80 success and 20 failure, right? So all the cases will be 100, this combination from 100, combination of 80 from 100, right? And for each particular sequence of outcomes, the probability will be p to the, sorry, this should be p to the 20 and 1 minus p to the 80, right? This makes sense, right? This is the Bernoulli experiments, N trials Bernoulli experiments likelihood, right? And then we use this model to model the likelihood of our observation, where we see 80 bulbs work and 20 don't. Any question? Everyone feels good? Okay. So now we have this model, right? We have this Bernoulli model, which can explain how well my choice of P will explain data, right? So you can view like you have a many hypotheses. Each hypothesis actually is represented by a particular p-value, right? You want to maximize the likelihood to find the best hypothesis, right? So what you need to do is maximize this likelihood, right? That means you maximize this N trial Bernoulli likelihood, right? And how can we do that? How can we maximize this thing with respect to P? Any hint? You mean you specify a set of p-values and pick up the one who has the largest likelihood? Yeah, this is something we need to clarify, right? So what we observed are indeed binary, right? We can say, okay, this particular light bulb works, this particular light bulb doesn't work, right? But the parameter we want to estimate from data is continuous. It's a continuous value between 0 and 1, right? It could be 0.2, it could be 0.8, it could be 0.99, right? So that means we can use gradient-based approach to maximize this, right? How can I do that, right? Suppose you have in general, suppose you have A bulbs work and B not work, right? And you find the hypothesis, meaning that you find a particular P which maximizes this likelihood. Okay? As we mentioned, maximizing a tiny small probability will always be a numerical problem. That's why we will take a logarithm to that, right? And it doesn't change the optimal value of P, right? You take a logarithm, and in our case, like the P of D given H is combination number P to the power of A, 1 minus P to the power of B, right? And this combination number we know is a constant to P, right? We can just get rid of it. Then our task amounts to maximizing logarithm of this guy, right? And you take the power in front of log, right? You get the objective to be A logarithm P plus B logarithm 1 minus P. Now how do we maximize this guy with respect to P? Any thought? Yeah, we can do stochastic gradient descent or gradient descent, right? But why not we just try to solve the gradient to be 0, right? We can do that. We can try that as well, right? If we take the derivative and set the derivative to be 0, you find that okay, the best P will be simply be the ratio of the failures, B over A plus B. Right? So you can see it's kind of surprisingly interpretable, right? It's just the ratio of the failures you observe from data. Right? But we need to point out the connection, right? This ratio is not just a heuristic. It comes from the maximum likelihood estimation. Okay. So this model was assumed to be a Bernoulli, right? You might probably want other models as well, right? Once you change to other models, you might not have this nice formula, or you might even not be able to solve the derivative to be 0. Then you might need to seek for stochastic gradient descent and gradient descent to find all the parameters. Okay, any questions so far? So next, let us look at another example, which is called normal distribution. Right? This is for usually used for continuous observations, right? So our previous example, we're looking at binary observations, right? And now suppose our data is continuous, right? We still want to find a hypothesis, right, that maximizes the likelihood. Okay. So here, we're assuming that our hypothesis space consists of real value functions, right? The input features are vectors of x of d-dimensional, and the output is a real number y. Okay. And here, this is our modeling procedure. Again, you can choose other modeling procedure, but here we just want to give you how common or most common used model. Right? We're gonna make the following model assumption. First, an input feature vector xi is drawn randomly, right? Say uniform at random. Then the true function, I mean, it's the target concept, right, is applied to get the prediction, right? Get true prediction f of xi, right? Of course, it's some kind of continuous value, right? However, you might not be in practice, you might not be directly observe the true value. The value is corrupted by some noises ei, right? And what you can observe is the corrupted target function value. Okay? And then how do we model this noise? Okay? A very commonly used model is to assume this noise comes from unknown Gaussian distribution with 0 mean. So that just means this noise is kind of like random, no bias. Okay? It's just perturbating surrounding 0. So if you write it down, it's like, okay, my training output, my training observation is decomposed as the ground truth function value plus some Gaussian noise, right? And this Gaussian noise follows 0 mean. Right? And say we have m such training examples, right, generated by this process, right? Then how do we model the likelihood of yi given f of xi? Suppose we have a hypothesis H, right? You got your hypothesis, right? You don't know where f is, right? But you have a hypothesis H, right? we want to know what is the probability that a particular output yi was generated by this hypothesis as h of xi, right? So that means, okay, suppose h of xi, h is the true hypothesis. Then the difference or the error in predicting yi, which can be written as yi subtracted by h of xi, right? Following our model assumption should be a Gaussian distribution, right? With mean zero and some standard deviation. At this point, let us assume we do not know what is the standard deviation of the Gaussian distribution of the noise, right? Then we can compute the probability or likelihood of observing one data point, xiyi, if it were generated using our hypothesis h. If you write down the formula, the likelihood of yi given h and input xi will be a Gaussian at this form, right? This is just Gaussian density. Okay. And sigma square represent the noise variance. And we further assume that, okay, all the training examples are drawn independently, right? So we can write down the likelihood of the whole data set, whole training data set, right? Which is just the product of each Gaussian likelihood here, right? Any questions so far? Right. So here, key assumption is that, okay, we're gonna assume that if your hypothesis is true, it's true concept, then the likelihood follows Gaussian, because we assume there's a Gaussian noise that corrupt the ground truth prediction, right? Now, given this likelihood model, right, our goal is to find the most likely hypothesis, a best hypothesis from the hypothesis space H. That means we just need to maximize the hypothesis over the hypothesis space, maximize likelihood of the data given each hypothesis over the entire hypothesis space. Right? So this is a product of the likelihood for every training output, training observation, right? If we just substitute the likelihood for substitute the Gaussian likelihood Gaussian form for the likelihood, right? It will take this form, right? And how do we maximize this expression? Yes, we don't want to really deal with a large number of products, right? To be more numerically stable, we take a logarithm to simplify. That means we're gonna maximize logarithm of this product. We know log product is a summation of the log, right? So just move, you could just change product to be the sum and apply logarithm over each Gaussian density, which can be further written as logarithm of this normalization constant subtracted by logarithm of exponential to some power. So it cancels. So you have a minus yi subtracted by, this is just the power in the exponential function, right? In the Gaussian density, which is minus yi subtracted by your prediction made by hypothesis h, take square and divided by 2 sigma squared, right? Again, the first term is constant to h, right? So it doesn't affect the maximization procedure. So you can just throw it out. Then in terms of that, we're gonna maximize the summation of the square error for the h and divided by this 2 sigma square, right? Again, 2 sigma square, although it is unknown, but it's constant to h, right? We can get rid of h as well, which doesn't affect the maximum, right? So eventually we'll see that your maximize likelihood estimation is equivalent to minimizing a square loss over the trained data, right? In other words, the most likely hypothesis is the hypothesis whose square error over the whole training data is the smallest. If we further consider some detailed hypothesis space, namely, I'm considering question. Yeah. It comes from our previous modeling, right? Our key modeling is that, okay, suppose you know the prediction from the ground truth function, right? Then your observation yi comes from a random Gaussian noise corruption over the ground truth prediction, right? And this noise has zero mean. In other words, the difference between yi and the ground truth prediction should follow a zero mean Gaussian, right? That's our key model assumption. And now we based on this assumption to calculate the likelihood of each of the data set given each hypothesis, right? When we calculate likelihood, we're assuming that, okay, suppose this particular H is the ground truth, then what is likelihood? You're gonna assume your H is the true F, then what is the likelihood of yi, right? And then it is a Gaussian, right? But of course, your H does not really necessarily to be the true hypothesis. Right? That's why we should run those hypotheses and find the one who has the largest likelihood, and we kind of assume that, okay, this one could be the closest to the true target function. Okay, any other question? Okay. Okay. Going back, right? We found that after taking logarithm and throw out a bunch of constant, we found that the most likely hypothesis or the best hypothesis, right, actually is the one who has the minimum square loss on the training data, right? And if we further give some detailed design about the hypothesis space, for example, I choose my hypothesis space to be linear functions, right? So that means each H is represented as a linear function of the input feature vector xi, right? Now, we substitute the form of hypothesis into our maximum likelihood estimation, right? We found that your best hypothesis comes from the hypothesis whose V vector has the least mean square error on the training data. So now we give the link between the least mean square of the linear regression we discussed before and Bayesian learning. Okay. Actually, you can view it as a probabilistic explanation for least mean square regression. Any questions so far? Oh, great. So now we'd like to give two views of the same objective function we have seen here, right? One is to view it as loss minimization perspective, right? We want to minimize the difference between the square loss error of our prediction, right? We minimize the total square loss defined over training data. That means, okay, we want to find out a hypothesis which best fits the training data, right? That gives us this least mean square objective function, right? And we can also explain it in from a different perspective, namely the Bayesian perspective, right? This Bayesian perspective assumes that the errors are normally distributed with zero mean and some fixed variance, right? Now, if we do maximum likelihood estimation on the linear hypothesis space, our best hypothesis is obtained or is found by minimizing this mean square objective function as well. So actually, this is just one coincidence between non-Bayesian learning and Bayesian learning. There are actually many such kind of connections. Nearly every Bayesian learning model can find out a nonlinear, non-Bayesian counterpart. For example, if I have some loss term, right, plus some regularization term. Please forgive my bad writing here. Regularization part, right? Like in SVM, this regularization will be just half of the square norm of W, right? And this could be the hinge loss, right? This also has a Bayesian counterpart, where you put some Gaussian prior distribution over the weight vector, and it has some corresponding likelihood whose logarithm corresponding to this loss term. Right? So the Bayesian learning framework has the benefit that, okay, you can come out a variety of prior distributions. Right? Once you take the logarithm over that, it actually turns to some regularization term. Right? And of course, you can design all kinds of data likelihood, and when you put the logarithm, it corresponds to the loss term, which matters how well it fit it. So that's why many models, even they were designed based upon some non-Bayesian motivation, right? You can convert it into a Bayesian model. Okay, so we're gonna finish our today's lecture by the brief summary. So we introduce the notion of Bayesian learning, right? We introduce two notions of Bayesian learning. One is just learn a probabilistic concept. That is, we learn mapping from the input feature vector to a probability, which is between 0 and 1, rather than just the discrete label 0 or 1 or -1, right? This will give us the confidence and give us more room to adjust how we're gonna make a decision about 1 and 0, right? And second notion of Bayesian learning is to use probabilistic criterion to model the hypothesis search procedure, right? So the benefit is that, okay, we can assign some prior distribution which encode our prior preferences over the hypothesis before we send the data. And then we build up a probabilistic link between the hypothesis and data, which we call likelihood, right? Then we can do map estimation, we can do maximum A posterior estimation to find the best hypothesis, right? And also we saw two concrete examples of maximal likelihood estimation. One is based on a binomial distribution. The other is based on normal distribution, right? Those two distributions are commonly used to deal with binary observations and continuous observations, right? And after this discussion, we expect that you'll be able to apply both map estimation and MLE, maximum likelihood estimation, to simple problems. Okay, any questions so far? Everyone's comfortable? Okay, I guess we can stop earlier today and have a great Thanksgiving holiday. I will see you on next Tuesday.